Today, let's look at binomial distribution worksheet number 1, and I'm going to just work through it with you. You need to have a calculator out and ready to go as well as we go through this. Use the cumulative probabilities to find f of x, which is probability x equals little x for each possible value of x. Now, that's a lot of stuff in there, but if you look back here, we've got n and p, and if n is 5, then x could take any of the values between 0 and 5, counting by integers. Yesterday, we looked at the formula. The probability x equals k is n choose k times p to the k, 1 minus p to the n minus k. Now that formula works. Hopefully you're good with using it. Today, I'd like to show you the formula on the TI calculator that you can use as well. If you look on the calculator, under distributions, second distributions, that's second vars, and you go down to letter or number 0, it says binom PDF. The binomial PDF means the binomial probability density function or distribution function. And the arguments here are NPX. NPX. In other words, if I want to know the probability x equals 0, then what I can type in my calculator is binom PDF NPX. Binom PDF 5.40. Tells me that's 0.0776. I can simply repeat that process, binom PDF 5.41, and go through each of these, 0.2592, etc., etc. Since I'm going to have to do it several times, I can also utilize a list. So in my lists, I can let L1 be 0, 1, 2, 3, 4, and 5. And in L2, I can make it the binomial PDF of 5, 0.4, each of these values in L1. If I type that in L2, it's going to find all of these for me all at once. There's the values. Since L1 contains the sample space, all possible values, then I know that the numbers in L2 ought to add up to 1. If they don't add up to 1, then it means I've made some sort of mistake. A quick glance at it implies they probably will, so I'm in good shape. On question 2, it says now draw a histogram of that. Well, I've got the data right here. I could use my calculator to make a histogram. It's a histogram of L1. A histogram, change that dude to a histogram. And I want the X list to be L1 with a frequency of L2. Kind of got to tinker around a little bit because it wants it to be an alpha character. So take the alpha off and then change it to L2. You could just look at that graph that we did in part 1 and make a histogram of it. But if you do it this way, the X list is L1 and those occur L2 often. When you hit zoom 9, it gives you one big block. So you got to change the window and X scale is 1. Now when I hit graph, I see this. If this extra stuff over here bothers you, you can change the Y and you can trace and see that these numbers here are just like we got in the previous question. So you can graph this dude out over here on this worksheet. So the first one is 0.07. That's in here. 2592. That's up here. So on and so forth. So there's the histogram. Now it says compute the mean and the standard deviation. Now these are two new formulas I haven't shown you yet. The mean, or the expected value, is given by the formula NP, and the standard deviation, or the standard deviation of x, is the square root of N times P times 1 minus P, which you may recall I told you yesterday is sometimes written as Q. So it could be the square root of NPQ. So for this problem, N and P were 5 and 0.4. That multiplies to be 2. And the standard deviation is the square root of 5 times 0.4 times 0.6, which you can do on your calculator, or you can trust me, and here's what you get. So these are two new formulas that you've got, the formulas for the mean and the standard deviation. If you're using the worksheet I've given you, you see I've written them over there on the side. For each binomial variable x, with n is 14 and p is 0.8, find the following. Now let's start with number 2. To do number 2 here on the calculator, I'm going to just write a 1 and I'll skip it. To do number 2, the probability x is 8. I can do the formula that I told you earlier, 14 choose 8 times 0.8 with 8 successes, and then I've got 20% chance of a failure and 6 of those failures. Or you can simply use the calculator, and the function is the binom PDF of N, P, X. Of course, if I'm going too fast for you, pause the video and catch up for a second. So in the calculator, I go binom PDF, N, which is 14, P is 0.8, and I want exactly 8 successes. That gives me 0.0322. Now looking back at number 1, question 1 here says, what's the probability that x is less than or equal to 8? Well, you might have noticed when we looked at the distributions that there's one called binom CDF, and that C means the cumulative density function. So really what the TI has got built into it is this function. The probability x is less than or equal to 8 is the binom CDF of NPX, 14.88. Now you could do the PDF of 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1 plus 0, but obviously this way is much more efficient. So it's 14, 0.8, 8. And that's 0.0438. Or 0.0439. Now for a question like part 3, the question wants the probability x is greater than or equal to 12. The CDF function does less than or equal to. So I need to convert this problem into less than or equal to, which means it's the complement of everything that's not greater than or equal to 12, which means less than or equal to 11. The CDF is always less than or equal to. So this is 1 minus the binomial CDF of 14.8, 11. So on my calculator, that's 1 minus the binomial CDF, not the normal PDF, the binomial CDF of 14, 0.8, 11. .4481. Find the mean and the standard deviation here. I'll use those formulas I showed you before. The mean is N times P, which is 14 times 0.8, which is 11.2. And the standard deviation is the root of NPQ, which is the root of 14 times 0.8 times 0.2. And again, you can just trust me that these numbers work out right. To do number 5, I'm going to show you a couple different ways. First, or to do part 5. First, the problem, of course, is I want the x's that go from 9 to 13 inclusive. Some of you understand right off the bat that this means the probability x is less than or equal to 13 minus the probability x is less than or equal to 8. And you'll see that what we're actually looking for is what I've got typed right here on my calculator, the binomial CDF of 13 minus the binomial CDF of 8 to give you an answer of 0.9121 or 0.9122. For some people, this is really confusing, so I want to show you a different way. I think that most of us would see that this problem right here means 9 plus 10 plus 11 plus 12 plus 13. So another way that I've done it is in my lists. In L1, I wrote 9, 10, 11, 12, and 13. Then in L2, I made those the binomial PDF of 14, comma, 0.8, comma, L1, NPX. When I hit enter, it gives me the PDFs for each of these values. So now if I add up L2, I ought to get the same thing I got here. Hopefully this will work. Hot dog, there it is. Maybe that way makes sense to some of you. Problem 3, for the binomial distribution with n is 10, p is 0.3, find the probability of the following. What I'd like to do on these is write down the problem, and then I'm going to give you the answer here, and hopefully you can go back later and check and make sure that works out for you. So on number 1, 5 or more successes means x is greater than or equal to 5, which is not real easy to do on the calculator. I'd rather do this on my calculator. I know I'm going to go through these quickly, but you can perhaps check them on your own if you're having some issues with this. Binomial CDF of NPX. And that turns out to be 0.1503, I believe. Part 2, at most 2 successes. That means I could have no successes, 1 success, or 2 successes, which is this, which is the binomial CDF of NPX. Nope, not 4, 2. NPX, which is 0.3828. Again, CDF is just the accumulation of the PDFs. So I could find the PDF of 0, the PDF of 1, and the PDF of 2. If I was going to show work, that's what I would have to do. Writing down this calculator function is not really work, but it gets the job done with what we're trying right now. At least 1 success, which means 1 success or more, that's the complement of no successes. So that's 1 minus the binomial PDF of 10.30. Pretty good chance of that. And at least 50% successes. Well, this is just worded a little differently, but if I do something 10 times and I want at least 50% successes, I want 5 or more successes, which kind of looks like part 1 again. All right, let's look at problem number 4. Find the probability of 12 successes in 20 trials when the probability of success is 0.7. For these, I'm gonna show you the work so you can do it the way I would expect you to do it on a test or a quiz. 12 successes in 20 trials. So X is 12, N is 20, and P is 0.7. So the probability X equals 12 is 20, choose 12, times the probability of success, and I have a dozen successes, and the probability of failure, giving me 20 minus 12, or 8 failures. Now, even though I write that, I'm really going to work it this way, because this is so much quicker. Now, part 2 says I've got 8 failures in 20 trials when the probability of failure is 0.3. All right, so the probability of failure is, I need 20, choose 8, 30% chance of failure, and I've got 8 of those, 70% chance here, 12 of those. Lo and behold, that's exactly the same thing. Even if I chose to work it out, like this, binomial PDF of 20.38. It's the same answer. And part 3 says, why is it the same answer? Well, it's the same answer because success is in the eye of the beholder. These two problems are the same scenario looked at from opposite perspectives. Number 5, population of a large city is 60% African American. A jury of 12 is selected at random from the citizens of the city. What's the probability at most 3 African Americans are selected? What's the probability that at most 2 African Americans are expected? And what's the expected number of African Americans on the jury? And find the standard deviation as well. So for this, we know that the probability of success is 0.6, which I'm defining as success is choosing an African American. N is 12. And part 1, probability at most 3 African Americans are selected. So that's the binomial CDF of NPX, which I believe works out to be 0.015. Part 2 says what's the probability at most 2 African Americans are selected. Binomial CDF NPX. I'll give you a second. You do this one on your calculators. Make sure you know how to do it. Again, it's under second distributions, and this is binomial CDF. Third, find the mean or the expected value. That's N times P, which is 12 times 0.6. I would expect 60% of the 12 to be African American. That's 7.2. And the standard deviation is the root of NPQ. I think you can probably understand why the expected value is NP, 60% of 12. Understanding the standard deviation is a little bit more challenging. I don't expect you necessarily to understand where that comes from at this point. Just be able to use it. Plug numbers in. That's 12 times 0.6 times 0.4. I'm suspecting you could do this on your calculator. Number 6. Suppose, for purpose of argument, 20% of the otters in a large aquatic community are infected with a parasite. A biologist samples 16 otters at random and records for each whether or not the animal is infected. Find the mean number of infected otters in the sample. Again, the mean number, the expected value, written either way, is NP, which is 16 times 20%, which is 3.2 otters. What's the probability exactly 20% of the otters will be infected, of the otters sampled will be infected? Well, 20% of 16 is 3.2. There's no way exactly 20% will be infected because I can't have 3.2 otters. What's the probability more than 50% of the sampled otters are infected? To get a better feel for this probability, compute its reciprocal. I kind of think the word reciprocal was a poor choice of words for the worksheet. Reciprocal is not really the right word. Complement, I think, is what they're looking for here. And so what we've got is the probability more than 50%. There's 16 of them. That means more than 8 of them are infected. So let's instead find the complement of that, meaning less than or equal to 8 are infected. So this is 1 minus the binom CDF of NPX, which is 1 minus 0.9985, which is 0.0015. Hopefully you're able to calculate these on your own, even though I'm doing them up here for you. You need to make sure you know how to do that. Finally, number 4, suppose in fact that more than 50% of the sampled otters are infected. How might the biologist respond to some such information? Use the probability of part D, and again I think they mean part 3, to support your argument. Well, on part 3 we found it extremely unlikely that more than 50% of the otters would be infected. If, lo and behold, more than 50% of the otters are infected, the biologist might say something like, whoa, this is weird. There's probably 2 options. Maybe more than 20% of the population is infected. That would explain getting a higher rate of infection than I thought. If it wasn't really 20%. Or maybe my sampling method stinks. Maybe I shouldn't just sample the otters that wash up on the shore, but I should figure out a better way to actually get a random sample of collecting the otters. And finally, question number 7. When an assembly machine is calibrated properly, approximately 5% of the finished products are defective. Periodically, the quality control engineer randomly selects 20 products and tests them. He'll halt the production line to check and reconfigure the calibration of any tested of any of if any of the tested products are defective. Assuming the machine is properly calibrated, in other words, assuming the probability of a defective product is 5%, what's the probability that we have to halt the production? Well, we halt the production again if the number of defected items is greater than or equal to 1, which is the complement of this, which of course is the same thing as this. So I want to find the binomial PDF of 20.05x. A pretty good chance that in this group I'm going to have to stop and recalibrate the machine. Hopefully this worksheet gave you a little better understanding of the binomial distribution. If not, perhaps you can rewind it and watch it again.